As part of my degree, I did a research internship at the statistical physics job at KU Leuven. It lasted 3 months and is titled Blues Traveling Wave Approximants for the Fisher equation. Before I dissect the title a bit, I would like to start with the motivation. I think most of us were explained how to model a pandemic these 2 last years, maybe even too much. However, I would like to touch it one last time. For those who are not familiar, the SIRS, or susceptible, infected, recovered, susceptible, is a compartmental model, which means that the population is assigned to compartment with labels. For example, S, I, and R stand for susceptible, infectious, and recovered. People may progress between the compartments. In our case, we have the SIRS model. So the susceptible can become infectious, the infectious can recover, and the recover can then become susceptible again. Also, in addition, the total population, so the total sum of the compartments, can grow by virtue of a constant birth rate. Not only grow, but can change by virtue of a constant birth rate or a decay through a natural death. Okay, the problem can be written down as actually as a coupled ODE, or ODE stands for ordinary differential equation. However, the thing is to take away that it has many parameters. It has a birth rate, a death rate, a vaccination probability, infectious probability, and so forth. Hence, it has a large phase space, or the dimension of the phase space is very large. This gives problems when trying to solve the system for ordinary differential equations numerically. You must run the solver, the numerical solver, then over and over and over again for different combinations of the parameters to understand the whole system. Can this then not be done more efficient? Most of the times you cannot solve the system analytically, but we could try to find analytical approximants. If such approximants could be found and are reasonably good, it is only plug and play. The problem remains that these approximants have to be decent. For example, for the SIRS model, the widely used technique to find analytical solutions of the coupled ordinary differential equations fail. That is, they do not give good converging approximate solutions. Often, these are iteration methods, and one will need an infinite amount of iterations to have a convergence over the whole domain. However, my supervisor for the internship and his team developed a new method to tackle the problem. The method is called BLUES. And look, for this specific model, BLUES provides a perfectly approximate on the whole domain for only the 3rd iteration. Of course, I showed you a specific problem where the method works very well. However, the approach of BLUES is very different with respect to the other methods, and hence, by this example, really shows its power. You're probably now thinking, what is the catch? Now, it will be a computational complexity, but more about this later. Now that I've showed you the why and what BLUES provides, let us dissect the title. BLUES stands for Beyond Linear Use of Equation Superposition, and it will be clear why, or will be clear later why. And it is a method to find an approximate analytical solution to nonlinear differential equations. This can be ODEs, which I already said is ordinary differential equations, coupled ODEs, and PDEs, which stands for partial differential equations. It was developed by Jonas Berx and Professor Indekeu, which can be seen here on the left. I'm going to apply this method to the Fisher equation, which is a reaction diffusion equation where we have the normal heat equation with an extra nonlinear term, which is here. The equation is used in modeling of the growth and diffusion of biological systems or physical active matter. Now, the nonlinear term provides 2 stationary states, at U or the solution equal to 1, and at U the solution equal to 0, which respectively represents the saturated concentration or the vanishing concentration of the system. The saturated concentration is a stable stationary state, and the vanishing concentration is an unstable state. Then the interplay between these 2 stationary states results that for certain initial conditions, we have a traveling wave solution that propagates to the right with a certain propagation velocity. Now, the thing I want you to remember is that the interesting part is that the stationary shape of the solution is actually non-analytical. And that is what we're going to try to approximate. Now, what defines a traveling wave or a wavefront for the Fisher equation? First of all, it must respect certain boundary conditions, which for the Fisher equation is 1 for x to minus infinity and 0 for x to infinity. Second, the shape of the wave must be stationary, or that is, it must be constant in time. And last, it has to have a constant propagation velocity. An important thing to understand is that there does not exist a technique at the moment which can produce a good approximant with these properties. And it's a thing to remember. Now, a second question one could ask is, for what initial conditions do we have a traveling wave solution? Now, there has been found that if the initial condition, which I will call f, lies in domain from 0 to 1, respects the boundary conditions, and has complex support, which is given then by this expression, then we have a traveling wave solution with a propagation speed equal to 2. A simple example could be then the Heaviside function, something that I took off my mind, which respect these properties, of course. Now, the goal will be to find approximants for this set of initial conditions for the Fisher equation. But first, let me give you a short introduction to blues. This is done by giving you a short recap to a technique we all know very well, and that is the Green's function method. Suppose we have a linear partial differential equation where we know that the function g, which I will call the Green's function, is a solution of this homogeneous differential equation. If this is the case, then we actually also know the solution of the same differential equation, but with an arbitrary source. And that is the solution is given by the convolution with the source and the Green's function. Now, the Blues method has a very similar structure. Consider the nonlinear partial differential equation here with a random initial condition, which I will again call f. Then the Blues method proposes a solution, which is of the form of the convolution of the Blues function and a source function phi. Both are undetermined, but we will see them what they become later. Then the question is, how do we find these two functions of these convolutions? What we do is we consider a suitable associated linear differential equation. Favorably, this linear partial differential equation is very similar to the nonlinear one. Then we take the Blues function b to be the Green's function of the linear partial differential equation. And if we then reconstruct a residual operator and apply it to the convolution, we can construct an identity for the function phi, which is actually something we are trying to find. However, this is a recursive function. Nevertheless, if we rearrange and convolve it with the Blues function, we can rewrite it in an expression for the solution of the nonlinear differential equation. Still, this is recursive, but this can then be iterated, where we start the iteration from the solution of the linear differential equation. The handy part will be that after some iterations, if the approximant is not to our liking, we can just start from a different associated linear differential equation and see if it gives better results. So we can have different starting points of our iteration. Now we can come back to the catch of the method. Taking the convolution analytically can be a daunting task. Often one comes across integrals that we cannot solve. However, it is when one takes linear differential equations that have more of the features of the nonlinear partial differential equations, the Green function becomes more complex, and thus the convolution is harder to solve. Hence, one has to balance the computational complexity and the convergence of the Blues method. This can be hard. At one time, it took me almost 2 weeks to compute some of the integrals, and Mathematica is no help here. Now we have a good understanding of what Blues entails. let us try to find Blue's approximant for the Fisher equation. As explained earlier, we could start from a different initial condition. We can start from different initial conditions and different linear partial differential equations. However, for the initial condition here in gray, we could not compute them analytically. Hence, the heavy side it is. But also, not every linear partial differential equation was useful. For example, the last linear partial differential equation does not contain information about the spatial diffusion. Consequently, the convolution is in the Blue's procedure will not smooth the initial condition, and a cornel will remain in every Blue's approximant, which is not a feature you want to have. Now, this is only, of course, if you use the Heaviside function, of course. Now, sadly, for the other linear partial differential equations, the approximant also does not yield good results, or it did not have did not respect the boundary conditions, or it did not converge to a constant shape. So instead, we tried something else. What if we enforce the boundary conditions by linearizing the nonlinear differential equation in two limits, that is, on the right and on the left side? You can see that then these solutions of the linear differential equations intersect, which I will call the intersection in moving junction. Hence, if you piecewise combine them, the result is actually quite good. And in fact, it already has the properties that a good approximant must have. It respects the boundary conditions by construction. It converges to a fixed shape, which is the exponential tail. And it converges to the same propagation velocity as the numerical solution. Now, maybe we can improve the result by iterating zero order or a linear result with the Blue's method. And indeed, this works. The left side gives a bad result, but the right follows the numerical solution better at small times. Furthermore, the previous properties we obtained are preserved if we again piecewise combine it with zero order from the right side, zero order from the right side. Okay. So I conclude by stating that using the Blue's methods on only one linear partial differential equation did not yield a good result. However, enforcing the boundary conditions with two linear partial differential equations yields a better result because it has three properties: the boundary condition, fixed shape in time, and constant propagation velocity. So the analytical expression, with this analytical expression, one can actually track the wavefront in time, and that's a handy feature to have. Nevertheless, we still have a spatial error which becomes constant, but we still have it at later times. Thank you for listening, and let us have a discussion.